What's up, everyone? So the flat Earth model often claims that the sun is small and local, maybe 3,000 miles up, maybe 100,000 miles up, nobody knows, but traveling in a circle over a flat plane. That leads to a measurable prediction. The farther the sun moves away from you, the smaller it should appear in the sky. So today, I'm going to test that claim using basic geometry, pixel measurements, and actual photos of the sun that I took. Now, full transparency, I've had overcast skies for the last few days, and that really put a damper in my plans. I wanted to do a 4-hour time gap, solar noon, so around 12:30, and then 4:30-ish, or exactly 4 hours later. Because of the overcast and having that happen, I'm using these old pictures. So these older pictures here, you can see kind of side by side here, were taken on August 29th of 2024. The solar noon one was at 12:26, and then the 10 a.m. was 10:21. So about 2-hour difference. Now, using dateandtime.com here, you can see in Phoenix, 12:28 was my solar noon, so it is about 2 minutes earlier than solar noon. But that'll be okay, because we're going to go off of where it was ground position. So here's how we're going to do this test. At both of those times, the sun is at a known GP, ground position, geographic position, whatever you want to call it. It's the spot directly under the sun on Earth, so 90 degrees straight up. Using those two times, we'll calculate the ground distance between the GPs, and that'll be the base of our right triangle. Then we'll assume the sun is certain heights, 100 miles, 1,000 miles, 10,000 miles, all the way up to 1,000,000 miles. That's going to be our vertical leg. With that, we'll use the Pythagorean theorem to find the hypotenuse, the distance from my location to the sun. So this is going to be the spreadsheet we're using. Now, because I want to do all the math a little easier and start with the closer position and compare it to the farther position, I'm doing the 12:26 before the 10:21 on everything here. So 12:26 will get the position of the sun. 10:21 will get the position of the sun. Close enough to my location because I don't want to give you my home coordinates. So this will be a few miles away from me. And then the ground distance away. Those few miles are going to be close enough where it shouldn't make a drastic difference. It shouldn't make any difference, really. And then we're going to go 100 miles all the way up to 1,000,000 miles in sun altitude. And then we'll do all the math there. So to get those positions, we'll start here. We've got the sun, Phoenix time, 12:26. And down here, we have the GP of the sun. So 8 degrees, 58 minutes north, 111 degrees, 19 minutes west. So we put that information here. I converted it to decimal degrees because the distance calculator I have uses decimal degrees. Then I couldn't get 10:21. It wouldn't load. So we'll do 10:20. And we have 8 degrees, 60 minutes north, which is basically 9 degrees north, and 79 degrees, 49 minutes west. The 10:21 position, this put 9, but I put it at 0.9999 so that it wasn't like an even flat number. And when I math it out here, it pretty much was that. It just defaults to this 9. And then for my coordinates, I am pretty much right near Tempe, so I did the Arizona Sun Devils Stadium. Now we'll use this distance between coordinates calculator here. I plugged in our 12 o'clock sun's GP and then my location, calculate the distance. And we've got 1,690.44 miles. Now we plug in our 10:30 times and we get 2,648.91 miles. So we plug both of those right here. So now, even before we make our entire prediction or a full prediction, we're going to get these heights in here so we can get the assumed distance to the sun. So what we'll do, we know that the sun's ground distance away from me at 12:26 was 1,690.44. We'll plug that in as B, and then the height, we'll say 100 miles. Calculate that, and we get 1,693.39. We'll plug that in for 100 miles. Change that to 500, and get 1,762.83. And now 1,000. So we're pretty much just going to go through this entire thing, grabbing this number here to the second decimal, plugging it in right here, and fill out this entire chart. There we go, we're done. So it's kind of cool because you can see that the farther we go out, the closer it becomes to this number here. And when I do 1,000,000, it's really funny because this is what the triangle looks like. So now we'll do the difference of these two in terms of miles. So this is unique to see. If the sun's only 100 miles up off the ground, it's almost 1,000-mile difference for that hypotenuse. But when the sun's 1,000,000 miles up off the ground, it's only a 2-mile difference. And then we're going to do the math here to find the change in percentage, because that will be kind of important. And we can kind of see the higher up we take the sun, the less it changes or should change in terms of size, really, and distance from us. Okay, so how does all this information help us? Easy. Perspective. If something moves farther away, it looks smaller. It's true of everything. Cars, planes, trees, houses, boats. So it should work with the sun and the moon. And that's why we're here today, to test the sun. Okay, so now we're going to get the size of these. Again, we've got our August 29th, 2024 picture. We'll start with the 1226 picture because on here we're kind of going with the closer one first. We're doing it the opposite that I wanted to do of suns above us moves farther away. We're going to do suns above us moved farther away, but the other way. So it was closer. It was farther, moved closer. We're just swapping those. What we'll do, we'll take our 1226 picture and open it in Paint. And then we're going to grab the edges here and shrink them down. And you can see as we shrink it, this number here will change. And I'm going to get them really close to the edges. And then we'll zoom in really close and get the line as close to the absolute edge as possible. So we got those. So let's go back up to the top, zoom in a ton, zoom in even more. Okay, and you can see it's a little grainy. So what I'm going to do is basically hit it on the first line where those pixels seem to like kind of be fuzzy. So we'll go right there. And we'll keep that consistent with all of the pictures, or both of the pictures, all of the edges. So we'll take that so that it's like right where it's grainy, down to the bottom. Take that up to that first graininess. Then over here. Take that to, this one's a little hard. So right there, I guess. So we've got 2045 by 2043. So we'll put those in here, 2045 by 2043. And then I'm going to multiply these so that we get the area. Granted, we're doing the area of a square essentially, but using the picture of a circle. But that should be okay because we're not, even though this is blank space, it's not really the sun. We're still getting the size of across this way. Zoom out there. Across this way and across this way. Actually, before we do this one, so now we'll make the prediction. This one here isn't double the distance. It's 1.5 times the distance, just over. So we're going to use that and the square law. But because we're going off of area, it's going to be a double the distance, quarter the size. So you can kind of see it here. So double the distance, 1/4 the size when we're going off of area. And that's what we're using here. So we'll do this math. Like I stated earlier, all of these numbers were kind of just so that we had some visuals and some ideas with the numbers. But here's the math itself. We have the original size times the change in distance squared. And that got us 1,705,002 pixels should be the area for this here. And we'll drag that formula all the way across. Double check that it held this, but dragged those over. So these are the predictions for how much the sun should change with the changes in this distance here. So now let's do the 1021 observation. We're going to do the same thing. We're just going to open it in Paint and drag the sides over, and I'm going to fast forward through this section. Okay, so we've got 2050 by 2046. That's pretty interesting because we can see right here, as the sun got closer, it shrunk. But this is probably user error and atmospheric conditions causing a little bit of fluctuation on the edge of the sun there. So that is our area of the first picture, the earlier picture, but farther away. So out of curiosity, we're going to do the math here and see that it is a 0.39% change in size. Like I said, it actually got bigger by 0.39%. But this is what we're looking for. So this is the angular size that we got. Do any of these, I need to paste that like normal. So now we just go, well, which one's closest? None of these are. Well, this one is the closest in terms of predicted size. So looking at this and using our knowledge and our abilities and all the math we can and measurements, we can see that we can estimate that the sun is more than 1 million miles away. Just for shits and giggles, the sun's 93 million miles away. So let's do the math with that one. So we have a little tiny bit of change here with the decimals. Let's move these over. Let's move this one over. And yeah, it doesn't get close. So I'm going to guess a little bit of this measurement was user error. So the takeaway, what does all this information tell us? If the sun were small and local, just a few hundred or 1,000 miles away, we'd see a noticeable change in size as it moved across the sky. We definitely should see a noticeable change in size as it moved across the sky with the inverse square law and the law of perspective that we see with every single thing that we have in reality. But we don't see that. The sun stays nearly the same size, exactly what we'd expect with a faraway sun. And looking here, we can see the sun's at least 1 million miles away, but we don't get much of a difference between 1 million and 93 million with my kind of math estimation here. So once again, the flat Earth model predicts the wrong outcome. While the globe model, it's weird. It matches what we actually observe. So now if you see that I did something wrong here or misled anything, awesome. By all means, tell me where I messed up. Challenge the method, challenge the numbers, or even better, do it yourself. Grab your own photos, use the triangle math, calculate the expected shrinkage, and show your results. That's how testing works. Not just making a claim, but putting them to the test. So always question the claim and test the evidence. Because if the model falls apart under a little bit of sunlight, it might not be the correct model.